The ionization of a weak base is incomplete and is treated in the same way as the ionization of a weak acid. We may represent a weak base as B. In the ionization process, it accepts H plus from water to become its conjugate acid Hb plus. Water, which serves as the acid, becomes the conjugate base hydroxide ion after donating its H plus to the base B. Kb equals the concentration of the conjugate acid Hb plus times the concentration of hydroxide ion divided by the concentration of the base B. Kb is called the base ionization constant. It is also a special case of Kc. Instead of the subscript C, the letter B is used in Kb to denote base. The larger the value of Kb, the stronger the base. Here are base ionization constants, Kb, of some bases. You are not required to memorize these. Some of these ought to look familiar to you as you learnt about them in Chapter 7. Ethylamine and methylamine are the common names of the aliphatic amines, ethanamine and methanamine, respectively. Aniline is an aromatic amine. Pyridine is the solvent used in the iron 3 chloride test for phenols. As mentioned in Chapter 7, all the amines are weak bases, but the aliphatic amines are stronger bases than aromatic amines. Now you can convince yourselves of this when you see their Kb values. Urea is a diamide. In Chapter 7, you also learned that amides are neutral. The structure of urea shown here isn't fully representative of urea. There are other resonance structures of urea. Once other resonance structures with a double bond between nitrogen and carbon are taken into account, a resonance hybrid structure may be formed. In the resonance hybrid, the lone pair of nitrogen is absent and therefore not available for accepting H+. Hence, its very low Kb value means that it is very, very weakly basic. It is so weakly basic that many do not even consider it a base. Here is an example. What is the pH of a 0.040 molar ammonia solution at 25 degrees Celsius, given that its Kb is 1.8 times 10 to the power of -5 at this temperature? First, recall that ammonia is a weak base. If you can't remember that, notice that the Kb value is smaller than 1. This signals that ammonia is not completely ionized in solution. Therefore, it is a weak base, which means we should construct an ice table where we eventually express all equilibrium concentrations in terms of the unknown x. Plug these equilibrium concentrations into the equilibrium expression for Kb and solve for x. From the value of x, determine the pOH first, then calculate pH. Write the Kb expression. It is Kb equals ammonium ion concentration times hydroxide ion concentration divided by aqueous ammonia concentration. The equilibrium concentrations from the last row of the ice table are then substituted into the equilibrium expression of Kb. We get x times x divided by 0.040 minus x. Equate this to the given Kb value of 1.8 times 10 to the power of -5. 10 to the power of -5 is rather small, so we use the approximation method. That is, Kb is less than 0.001, so 0.040 minus x is approximately equal to 0.040. Solving for x becomes easier and faster. X is 8.5 times 10 to the power of -4 molar. All of this is really mechanical, and some stop here once they get a value of x. But the question isn't asking for x. It is asking for pH, so we need to interpret the meaning of x. It is the concentration of hydroxide ion according to the ice table. We input this value of x into the pOH formula to get 3.07. Finally, we can find pH, knowing that pH plus pOH is equal to 14.00. pH is therefore 10.93. Here is another example. Caffeine, the stimulant in coffee and tea, is a weak base that ionizes in water according to the equation shown. A 0.15 molar solution of caffeine at 25 degrees Celsius has a pH of 8.45. Determine the Kb of caffeine. Use pH to determine pOH and pOH to determine the hydroxide ion concentration. From the hydroxide ion concentration, use reaction stoichiometry to determine the other equilibrium concentrations and plug those concentrations into the equilibrium expression to evaluate Kb. By subtracting 8.45 from 14.00, we get the pOH value of 5.55. The hydroxide ion concentration is equal to 10 to the power of negative 5.55, which is 2.82 times 10 to the power of negative 6 molar. We come up with the ice table. 0.15 molar is the initial concentration of unionized caffeine. At the start, ionization has not yet begun, so the initial concentrations of the protonated form of caffeine and hydroxide ion are 0 molar. The system addresses the problem of missing products by getting caffeine to ionize. Hence, the change in concentration C for caffeine is minus X molar, while the change in concentration for protonated caffeine ion is plus X molar, and that of hydroxide ion is plus X molar too. To get the equilibrium concentrations, we add the entries of I and C. So the equilibrium concentrations of caffeine, protonated caffeine ion, and hydroxide ion are 0.15 minus X, X, and X respectively. However, we have already worked out the hydroxide ion concentration and found it to be 2.82 times 10 to the power of negative 6 molar. This is the equilibrium concentration of hydroxide ion, and it is the value of X. So we replace all the X's in the ice table with 2.82 times 10 to the power of negative 6 molar. We write the equilibrium expression for Kb, which is the concentration of protonated caffeine ion times the concentration of hydroxide ion divided by the concentration of caffeine. Then by substituting all the numerical values from the last row of the ice table into the Kb expression, we get 5.3 times 10 to the power of negative 11.